You've seen this. Username, taken. John, taken. John_1, taken. John_1_real, taken. John 2007 final, available. Annoying, right? But that little message is hiding one of the hardest problems in computer science, searching billions of records in the time it takes to blink. Here's what most people assume. The app just asks the database, does John exist? And for a small app, that's exactly right. One table, one query, done in milliseconds. But Instagram has over 2 billion users. Thousands of checks arrive every second from every corner of the planet. At that scale, the simple answer breaks. The data won't fit on one machine. The traffic won't fit through one machine. Disk reads, network hops, queue delays, they pile up until your sign-up page takes 10 seconds to load. Users leave. So today, we build this system like a real engineer would. And here's the exact map of what you'll learn. A database, sharded across thousands of machines, using consistent hashing to find any name instantly. A Redis cache cluster in front of it, answering repeat questions in microseconds. And at the very front, a Bloom filter, a probabilistic data structure that proves a name is free without storing any names at all. Database, cache, filter. We'll build them in that order and watch each one fix the last one's weakness. Let's start with the truth. Every system needs one place that holds the truth. For usernames, that's the database. Think of it as the guest book. If a name is in the book, it's taken. Final answer. So here's the first real question. 2 billion names, terabytes of user data. It physically cannot fit on one machine. The answer is sharding. Split the data into pieces, called shards, and spread them across thousands of machines. Each machine holds a small slice, and each slice is fast to search. But sharding creates a new problem. A check for John arrives. Which of the 1,000 machines has it? You can't ask all of them. And a giant table tracking where every name lives? That table becomes the bottleneck. Here's the elegant trick. Run the username through a hash function, a formula that turns any text into a number. John always produces the same number, and that number maps to exactly one server. Server 4821. No searching, no directory. The name's location is calculated, not looked up. Any server can do the math and instantly know where John lives. This is called consistent hashing. Picture all possible hash values arranged in a ring. Each server owns an arc of that ring. Your name's hash lands somewhere on the ring, and whoever owns that arc owns your name. Add a new server? It takes over a small arc, and only that slice of data moves. Everything else stays put. But wait, what if server 4821 dies? 2 billion users and John just vanishes? No. Every shard is replicated, 2 or 3 copies on different machines. One dies, a replica takes over. The ring heals and nobody notices. This is the backbone of Cassandra and DynamoDB. Sharding for scale, consistent hashing for routing, replication for survival. So storage, solved, but cost, not solved. Every lookup still crosses a network, still touches a disk, still burns CPU, thousands of times per second. And most of those queries are embarrassingly repetitive. Which raises a better question. Why are we looking up the same names over and over? Look at real traffic and there's a pattern. Username checks are massively skewed. John, Alex, Maria. Short words, celebrity names. A tiny fraction of names generates a huge share of all requests. Querying the database 1,000 times a minute for John? That's like Googling the same question every 5 minutes instead of just remembering the answer. Layer 2, a cache. Redis sitting in front of the database, storing recent answers. John, taken. And why is Redis so fast? 3 reasons. 1. Everything lives in RAM. No disk, ever. A RAM read costs nanoseconds. A disk read costs milliseconds. That's the difference between 1 second and 11 days. 2. It's a hash map. Key, the username. Value, a tiny flag. Lookup time is constant. One name or 1 billion names, same speed. 3. A single-threaded event loop. One thread handling requests one by one.
Sounds slow? It's the opposite. No locks, no waiting, no coordination overhead.
just pure sequential speed. The result? Over 100,000 lookups per second from a single Redis instance. But one instance isn't enough for Instagram. And what if that instance crashes? So Redis runs as a cluster. The key space is divided into hash slots, 16,000 of them. Each Redis node owns a range of slots. John gets hashed to slot 11,442, and whichever node owns that slot answers. Sound familiar? It's consistent hashing again. Same trick, second layer. And each node has a replica. If a node dies, the replica is promoted, and the cache keeps breathing. One more limit. RAM is expensive, and you can't cache everything forever. So Redis evicts. Least recently used entries are pushed out, and hot entries stay. Still, there's one category the cache can't help: brand new names. Someone invents John X 2007 final. Nobody's ever asked, so it's a guaranteed cache miss, straight to the database. Millions of fresh names a day, each paying full price for an answer that's almost always, it's free. What if we could prove a name is free without storing any names at all? The strangest, cleverest layer, the Bloom filter. Fair warning, this one bends your brain a little. That's normal. Stay with me. Think of fingerprints on a glass door. Everyone who ever entered touched the glass in a few specific spots and left prints behind. Now, was John ever here? You don't need a photo. You don't need a logbook. You check his spots. If even one spot is clean, no print, he was never here. Physically impossible. Certainty from absence. Now let's build one, for real. Start small, an array of 10 bits, all zeros, and 3 hash functions. Each takes a name and outputs a position. Let's register John. Hash 1 says position 2. Hash 2 says position 5. Hash 3 says position 8. Flip those bits to 1. Now register Maria. Positions 1, 5, and 9. Flip them. And notice, position 5 was already 1. It just stays 1. The names themselves? Thrown away. Only their fingerprints remain. Now, someone checks Alex. Hash Alex, positions 2, 6, and 8. Position 2, 1. Position 8, 1. Position 6, 0. Alex was never registered. Guaranteed. Because registering Alex would have set bit 6. No database touched, no name stored. Definitely free. But now, check Sarah. Hash Sarah, positions 2, 5, and 9. Position 2, 1 from John. Position 5, 1 from John and Maria. Position 9, 1 from Maria. All 3 bits are set, so the filter says, probably taken. But Sarah was never registered. Her spots were covered by other people's fingerprints. That's a false positive. The filter's one weakness: it can be wrongly suspicious, but never wrongly confident. Free means free, always. Taken means go verify downstream. And that's fine, because a false positive just means one extra cache lookup. Annoying, not wrong. Now scale it up. Not 10 bits, billions of bits. Not 3 hash functions, 7. 2 billion usernames at a 1% false positive rate in about 1.2 gigabytes. Smaller than a movie download. Small enough to sit in the RAM of every application server. One quirk though, you can't delete from a Bloom filter. Bits are shared between names. Unset John's bits and you might erase Maria too. So filters get rebuilt, periodically from the database in the background. A fresh filter synced to the truth. And with that, the front door is complete. Most checks, every fresh creative name, end right here. Under a microsecond. The cache and database never even hear about it. Now, here's the beautiful part. We built this system top-down. Database, then cache, then filter. But a real request experiences in reverse. You type John and hit check. First, a global load balancer. DNS routing sends you to the nearest data center. From Dhaka, you'd hit Singapore or Mumbai, not Virginia. Inside that data center, a local load balancer knows which servers are healthy, which are overloaded, picks one, and hands over your request. On that server, the Bloom filter answers first. Definitely free? Done, in microseconds. Maybe? The Redis cluster checks its memory. Hit, done. Miss. Consistent hashing points to one shard, one machine among thousands that holds the truth. And the answer is cached on the way back. Filter, cache, database. Each layer exists to protect the one behind it.